All right, I want to end with just setting one more of these things up, and we're going to add one more curveball here. I'm going to show, for the first time, us finding a volume of revolution by taking a two-dimensional region and spinning it around something other than the x-axis. And let's see how that changes things. So let's take a look at a couple of functions. So I've got a straight line, x plus 3, and then I have an upside-down parabola, negative x minus 2 squared plus 2. So it's moving 2 units to the right and 2 units up. And what I'm interested in doing is this. So here it is. I want to set up an integral expression. So notice that it's an expression and not an equation. I'm setting up some expression without an equal sign to find the volume of the region that's bound by f of x and g of x, and x equals 1 and x equals 3 around y equals negative 2. Whoa, so let's unpack what this is saying. X equals 1 and x equals 3 are added here to the list of functions. So the area between these two curves as it stands right now is infinite, right? I mean, there's no bounds on these things. There's no starting point and stopping point, and they never intersect. So that's what this x equals 1 and x equals 3 is giving us. A vertical line at x equals 1 and at x equals 3 now bounds this region up so that it is a finite two-dimensional region. So my goal is to take this two-dimensional region and spin it. It says that I'm going to spin it around the line y equals negative 2. And I should have used the words rotated or spun or revolved around y equals 2. But the idea here is that y equals negative 2 is going to become our new axis of revolution. So I'm going to draw that in. I'm going to erase some of this other stuff so that I can show that. So let's clean this up a little bit. I'll leave that sitting there. So this is the parabola. So negative 2 on the y-axis is right here. And this is my new axis of revolution, my AOR, axis of revolution. So I'm going to take this two-dimensional shape and I'm going to spin it all the way around this line. And if I were to look at the far side, the lower part of this thing after it spins, it should look something like this. And by the way, to help myself out with this, I'm just going to do some simple counting here. The distance on my far right side at negative 3 here, the distance from my axis of revolution all the way up to the top point here is going to be that distance, which is 6. I can find that out by just plugging 3 into my function. 3 plus 3 is 6, plus this gap of 2. So it is 8 units away. So now I'm going to go 8 units south of this. Whoopsies. 1, 2, 3, 4, 5, 6, 7, 8, and make my new point right around there. In the same way, just for another reference point, this is the point 1, 4. I can plug 1 into my line function and get 1 plus 3, which is 4. So that distance is 4, but the distance down to the axis of rotation is an additional 2, so it's 6. So I'm going to go 6 units below my axis of revolution. So 1, 2, 3, 4, 5, 6, and make another point there. And this line is going to be this portion, this green portion right here that I'm coloring in, that thing after it's spun all the way down south around this axis of revolution. And then just to get another couple more points here quick, this that's a distance of 2. An additional 2 down to our axis of revolution is 4. So I'm going to go 1, 2, 3, 4, make another point, and then I'm just going to kind of go in the same reference. I'm going to just go one up and over in either direction to get this little curve. And this is all just trying to help me to see, I'm just trying to see what this thing is going to look like. So here is the equivalent shaded region. Looks a little bit rough, but that is the red shaded region from above after I've flopped it down over the axis of revolution. So if you can picture this part that's created when we spin this thing around, it's got a flat top, a flat face, on either side, right? A flat face, and then the outer edge is this angled piece, which I'm drawing here. That's from our line. And here's the flat face. And then the inside walls of this thing are interesting. They're sort of this like weird dished out sort of deal, right? From the parabola. So this is getting super weird. I'm just going to make these solid lines, even though these lines that I'm drawing right now are actually the inside walls. So if you can picture this, these are the inside walls of this weird kind of conical tubular sort of section. Yeah, and then so we would have, our inside. This is exceedingly difficult to draw, but we have that inside circle as well. So hopefully you're kind of seeing roughly what this thing would look like. The idea, though, is that if we take a cross section, if we slice, 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 slice down the center, and we take out this big piece, we're going to be looking at a giant washer, right? The face is going to be kind of small in relation to the rest of the thing, and so we're going to have to figure out what is the area of that face. And just like last time, it's going to be big R squared minus little r squared. The big circle, the area of the big circle is pi r squared. The area of the little circle is pi little r squared, so we're trying to extract all of this red portion. So let's start with what we know. The limits of integration are going to go from 1 to 3. That was given to us by our extra lines. And now we've got a of x dx dx, which, like we just mentioned, is going to be pi times big R squared minus pi times little r squared dx. So the question again is, what is big R? What is the distance that is the big radius? And what we need to think here now is that if we look at this picture, the distance, I'll start here at the axis of rotation. Always start on the axis. You want to figure out what is the distance all the way down to the outer edge, or all the way up to the outer edge. It's the same distance, right? And this is where we need to be careful. The distance from the x-axis up to the outer edge, that is given by the curve x plus 3, or by the line x plus 3. That's the distance from the x-axis, but that is not the distance to the axis of rotation. To get this additional distance, just like we did when we were flipping the points around, I've got to add an additional 2 units. So the distance to anywhere along this outer edge is going to be x plus 3 plus a bonus 2 to cover this distance. So what I'm saying here is that big R, I'm going to write these over here on the left, big R is equal to x plus 3 plus 2, which of course is equal to x plus 5. Little r, we're going to play the same game, and it's going to be the distance up to this curve, which we want to say is just negative x minus 2 squared plus 2, but there's an additional 2 units. An additional 2 units, so I've got to add that additional 2 units. So it's negative x minus 2 squared plus 2 plus 2. So negative x minus 2 squared plus 4. So there we go. And using this information, I'll be able to set up my integral. I'm going to just pull the pi out front again. From 1 to 3 of big R squared, so x plus 5 squared minus, in parentheses, negative x minus 2 squared plus 4. All of that little r is all being squared. And then the dx again indicates that we are spinning in the x direction. So here we go. I'm not going to take the time to solve that thing, but that is our integral that we would set up. So you've got 2 new bits of information. You've got washers. You've got to take the big R squared minus the little r squared. And now we have the complicating factor of having an axis of rotation that is something other than the x-axis. And in an example like this, we would need to add that distance. We're going to see in class some examples where we might need to subtract some distances or do some other weird things. Every situation is going to be a little bit unique, and we're going to have to rely on some artwork and some pictures and some graphs to try to figure out how do we find the distance of the big radius, and how do we find the distance of the little radius? All right. Adios.